So, welcome back again. Post lunch session, difficult session to stay awake. So, please try to stay awake. A lot of interesting things will be there. So, we stopped at a place from where we can leap onto the core area of the pumping, right. So, now let us see the relative centrifugal pump characteristics with clear water and mineral slurry. This is relative. What do you see? This is the head axis, this is the Q axis, right, that is a flow axis, this is the head axis. You can see two curves, one is the water and the other is the slurry. Here also power same, power, you just see the fun. In the head, this color, that is the slurry goes down, power it goes up, efficiency the slurry goes down, water is up. Now let us see, against a particular this speed, if I plot a particular Q, the head is less for the slurry compared to the water. Why? Because of the slip, because of the rheology of the slurry. So, the way the fluid is sucked in as far as it goes to the water, and the way the fluid will be sucked in when it is a slurry will pose more resistance, right. So, the head developed will be lesser, efficiency will also drop. And what happens for the power? If it is a less efficient machine, it will take higher power. So that means it is very interesting, very important that slurry head and water head are not identical. Slurry head and water head are not identical. All the pump testing or all the pump curves which you will see in the manufacturer's catalogs are all clear water pump test curves, and your application is a slurry. So, there is a big gap between the two. So, the question comes, you got to calculate it in terms of slurry, then eventually take it to the water. Then based on your water, he will take where the point will come, against that what are the other features that will be coming there. But do not confuse with the slurry head and the water head. These are two different things. You will compute it in the slurry head, transfer it back to the water head, right. This is a big challenge. How does the curve look like? The centrifugal pump characteristic curve. You see here, at different speeds the curves are going like this. These are the curves, the efficiency curves, okay. And the red one is the BP, okay, best efficiency point. We discussed in the morning what is BP. So, against particular speed you have a BP point which tells you what is the best flow, right. And these are the curves, you have the NPSHR curves, okay. So, here you see it is up to 90 meter head and flow up to 7000 meter cube per hour, the range, right. If you look here, impeller diameter 910 is a big pump. Passing sphere, I said this one, that between the vane we talk about that the width of the vane spacing is described in terms of the sphere, right. Impeller type 5 vane closed, we have discussed about closed impeller, open impeller, it is a 5 vane. Inlet diameter, outlet diameter, okay. So, all these things will be there in a pump characteristic curve, the typical pump characteristics curve. Next we go to another curve very similar to that, but remember flow 7000, head 90 here. Next one, you are talking about 150 and flow 2500. That means it is a high head low capacity pump, high head low capacity pump. Look here, inlet diameter 300, outlet 250. Can you see here that inlet diameter is more compared to the outlet? Why? Sorry? Suction, why the suction is bigger? It has to help you to provide better NPSHA. Better NPSHA. Okay? And it will also make the eye bigger, so that bigger amount of slurry can be pulled in. Here also all the things are there, BP, efficiency lines, right, NPSH, everything is there. 910. Okay. Let us see another one. Here 765, 300 to 50. Now here 110 and 2500, it is a medium head, medium capacity, right. So, and the NPSH, these are the NPSHR efficiencies. You can see about 85% is the best, 87.5 is the best efficiency. Normally efficiency curves, if you see here, it is like this, it goes like this. These are the typical characteristic curves of the centrifugal pumps. These characteristic curves or whatever are there, all have been calculated or in the test rig, tested, and eventually affinity laws applied and calculated and then posted here. All are based on clear water. All are based on clear water. Operating point. What do we mean by the operating point? Because very often we say that we need to select a pump. To select a pump, what we need to do? We need to tell the pump manufacturer what is the Q, that is the flow rate I want, and at what is the head. These two are the basic things. So that means if this is the pump characteristic curve HQ and this is the system resistance curve, right. So the point at which they two coincide, that is the operating point. So operating point is the point of intersection of the system resistance curve and the pump HQ characteristic curve against any particular speed. So this is for a particular speed. There would be if we go up in the speed, the curves will shift up. We have seen it in the earlier diagrams. So now this is the static head. This is the static head and this is the variable head, that is the frictional head drop or other pressure heads if required, suppose there is a cyclone. So all these things are covered here, and this is the static head. Okay. So now the moment, these are the friction heads are proportional to V square by 2G. I can write the total friction head, it is proportional to frictional head is proportional to, or I can say is proportional to V square by 2G, or I can write HF equal to K V square by 2G, right. So why am I discussing this one? Why have I written this one? For what? This is the equation of a, what is the nature of this equation? Parabola. What is this? Sorry. What is this? Parabola. It's parabola, right? So, the nature of the parabola would be like this. Is it clear? Shape of the system resistance curve, is it clear? Now, let us see again. This system resistance curve is a parabola, right? Parabola can be of this order, that order, that order, all are parabola. Now, if it goes here, you get a particular Q1. If it goes here, you get particular Q2, which is higher. If it goes here, you get particular Q3, which is even higher. So, that means if I throttle the system, the curve shifts this way. If I throttle the system, the curve, system resistance curve shifts. Okay? Is it clear? Now, similarly, there are 3 speeds, let us say, and this is the system resistance curve. This is meeting the first speed here, second speed there, third speed there. That means, if I change the speed, my Q changes. So, that means again it is corroborating the affinity law. It is corroborating the affinity laws. These 2 points are clear. This will come as a precautionary measure at the last when we will discuss that. The trouble against any problem of the pump, either of these 2 steps, this will come. Now, this is the typical one. Total head is this. So, total head and total Q, the point is placed over here. Now, while placing the point, it may so happen that it falls within or on the pump characteristic curve. It may so happen that it lands in between the 2, any point where there is no speed mentioned. So, you got to calculate that speed where it is, and people tries to do one thing, they try to measure, okay, this gap is 100 RPM. So, that will be this is absolutely bogus, this is not the way to do it. Use affinity law, use affinity law to calculate the RPM. Okay. Typical characteristic curve for centrifugal pumps of different impeller sizes. Now, the earlier one which I have showed you, these are with different speeds. Now, here it is against a particular speed, but with different impeller diameter. This is also another way of expressing the pump characteristic curves. It is a typical water pump, speed, very high speed, all right. But normally the slurry pumps which we use, we do not get the characteristic curve or the point over there in this manner, we get it in the earlier manner, earlier as per the earlier pictures which I have shown you. That is more familiar in the mineral processing industry. Now, this is important. This is the linkage between specific your density, the percent solids, and by volume and percent solids weight by weight. So, that we have also seen, we have seen the linkages when I discussed the mill. So, this is another way of doing it, it also can be used. So, if one figure is known, the other can be known, provided the density of the solid is given, right. Now, this is important, selection of correct pipe size for the slurry transportation and estimation of friction losses, because out of the all things, static head is very simple, anybody can do it, but the problem comes in calculation of the friction losses, what you will do, how you will do. So, this is one method This method says that normally for a pipe size there are some standard velocities which are available, right? Critical velocity they say. So, below that you should not go. Now, for that you first of all you have a slurry. So, you pick up a particular pipe and see where you are exceeding this thing or you are not exceeding this thing, these values as per this chart, right. So, then you have selected a pipe and then the critical velocity of the slurry, they say that you have to make a correction on that actual velocity, transport velocity. What is that correction? You have to multiply that one by a factor which depends on the specific gravity of the solids. So, there is a curve. So, you got to pick up what is the specific gravity and against that what is the correction factor. Suppose here from the table he has calculated 2.4 meter initial, right. Now, after the correction it has become 1.7 meter per second, right. But if actual velocity he has picked up is 2.6 meter which is or 2.8 meter which is much higher. So, there is no problem as far as the settlement of the solids in the pipe is concerned. So, why they are doing it all these things? First of all you need to pick up what is the pipe size, what is the correct pipe size which will allow the slurry to be transported properly without any settlement of the solids. The biggest thing is this: if due to the low velocity or improper velocity the solid gets salted or deposited, then the transportation becomes a risky affair. Okay. So, to avoid that some methods are considered. So, this is one of the method, critical velocity method. So, you pick up a critical velocity and then you check actual and you decide the pipe size. Okay. Because for calculation of the friction losses pipe diameter is very important. Without the pipe diameter you can't do anything. You got to know the flow rate and the pipe diameter, both are equally important. But the most important, the earlier process is a thumb process we call, but this is the thing we call this as a more elaborate process of estimation of the settling velocity in the pipe. This is called the Durants limiting settling velocity. Durant was a professor in Colorado School of Mines. So, he did a lot of study and based on that a set of curves he developed depending on the CV of the slurry, that is a concentration volume by volume, 2%, 5%, 10%, 15%. This is for narrowly graded particle size. What do you mean by narrowly graded? You got to see the ratio of D80 by D20. D80 by D20, if D80 by D20 is less than, I would say less than 4, they are telling less than 2, then these set of curves are valid. So, what you need to do? You need to pick up the D50 size, whatever is the size, you need to pick up the volume, concentration, then go there, come here, just see what is the value of the FL, which is the limiting velocity settling velocity factor, limiting settling velocity factor, FL. FL needs to be computed. Now, he has got another curve. So, but this one has been modified by Cave. So, it is a Cave Durants modified curve, right. So, here the curves go like this and this is for widely graded particle size. That means, if your D80 by D20 exceeds 5, then this one is applicable, right. So, what is happening? You have got 5, 10, 20, 30 and there can be a 40 also, but he is telling that if it is a 40 you have to consider that as if it is 20, right. So, 30 is the most critical one, 30% solids volume by volume. If it is 40, it is better. Then you have to come back to 20% solid volume line and find out the FL. So 30% is the most crucial one for the pumping, volume by volume transportation.
That FL, how is it defined?
Sorry?
FL.
Huh?
How is it defined, that factor?
I am coming to that. How it is connected? Because first we have found out what is FL. Let us see how it is connected. Now, if you see there, Durant mooted the concept of appearance of the material settlement condition in case of horizontal transportation by a term known as the critical velocity VCR. It is a absolutely horizontal transportation, right. For that, this condition is applicable. As per Durant's recommendation, transportation velocity in the pipe must be greater than the critical velocity VCR to ensure deposition free slurry transportation. Now, VCR equal to FL into 2G D SGS minus SGL divided by SGL whole under square root bracket meter per second, where FL is the settling coefficient, we have seen it. SGL is the specific gravity of liquor, SGS is the specific gravity of the solids, G is this, and D is the inside diameter of the pipe. If you say, let us say 150 NB, I pick up a pipe size, I am telling that the pipe size is 150 NB nominal bore, then what is the value I should put here? 150? What is the value I should put? Shall I put 150 or something different? So, corresponding to 150, there is a pipe chart which will tell you what is the outside diameter, that is 168.3 is the outside diameter, minus 2 into wall thickness. So, that is the precisely the inside diameter of the pipe. So, that value has to be put in here, converted into meters to be put in here. Durant curves are to be used for closely graded particles, this, and modified Durant curves are to be used for that. Okay. Now, the important thing, look at this, if D increases, VCR increases. If D increases, VCR increases. So, that means if I take a 500 dia pipe, my settling velocity would be somewhere close to 4.6 meter per second. So, I have to select a velocity which is more than that, then it will be absolutely nonsense. That means the velocity will not at all be in the economic range, because such a high velocity would mean huge wear and tear and huge energy consumption in terms of the pumping cost. So, that is ruled out, that is ruled out. So, that is what it is there. As the pipe size increases to cater to the high flow rate requirement, VCR gets increased to impractical and uneconomical zones in terms of power consumption and wear. Therefore, so if that happens, what is the solution? Very often nowadays you get 1000 meter cube per hour, transport it 1000 meter cube per hour, the pipe size would be close to 400 NB, right. So, what do you do? Therefore, existing industry practice is to carry out the saltation check with the maximum value of VCR as 3 meter per second. First step, carry out a test. Test means put it there, use that value, calculate the pipe size, go to the next lower one to ensure that pipe velocity is even more, and put it in the Durant formula, check the critical velocity. If it is within 3, fine, stay with that. If it is not, if VCR is found to show higher values, the same is neglected and the economical pipe velocity less than equal to 3 meter per second is considered to size the pipe, right. So, that means we are neglecting Durant's thing. We are telling on one hand that it has to be seen, but we are saying that we are neglecting it. Then why? What we are doing? It is also ensured, at the same time it is also ensured that there would not be any horizontal run in the total pipe route. I would ensure that my total pipe route will not have any horizontal run, because the risk is for the horizontal run. if I can ensure that I am making a pipe route in a manner where there is no horizontal route, I am fine, absolutely fine, there is no problem. Otherwise, you have a problem. So, basically the Durants thing and for the horizontal transportation, normally pipe size of up to say 250 NB, we have seen that VCR is valid. So, for the horizontal pipe, you will see particularly for the tailing pipe etc., very rarely you will see that pipe diameters are going more than 250. If required, they will put 3 lines, because in the tailing you can't have horizontal length free route, you can't have. So, their horizontal travel will be there, saltation chances will be there. So, to negate that, you got to come down in the pipe size. So, probably it is a parallel pumping, right, or maybe either parallel pumping or pumping and branching, right, but it may be 2 lines going, 3 lines going, so that you can totally your size of the individual line stays within 250 NB. So, up to 250 NB, this one is valid. More you go up on the pipe diameter, this becomes unrealistic.
What's that nomenclature? 200 NB?
NB is the nominal bore. NB is the nominal bore. As per, if you go to the IS standard, Indian standard, there are 2 standards, IS 1239 part 1, which covers up to 150 NB, and IS 3589 that covers beyond 150 up to 500 NB. Okay. So, we have decided the pipe size, pipe dia. Now, we have to calculate the friction loss. Now, there is one method here. The friction losses are always calculated as percentage, 5% friction, 10% friction. That means so much meter per 100 meter of pipe run, right? It is calculated in that mode. So, you will see here the velocities are there, pipe sizes are there, and here is the flow rate. It could be liter per second. So, you climb up from there, touch your pipe size, go over there straight. So, this is the friction loss. Okay. Now, this is the friction loss for the clear water. Remember, this is the friction loss for the clear water, not for the slurry. Now, to convert it into the slurry, you have to use a correction factor. Here again, percent solids by volume, 30%. Take the 30% line, draw a straight line, wherever it is you are connecting with this line, drop a perpendicular down, pick up the correction factor, multiply that correction factor, right. So, here also you can see that initial value was this. Okay. So, for pipe length of 50 meter, 3 meter is coming as a friction head loss, clear water. Now, you multiply, this was 3 into 1.5 is a factor. So, 4.5 meter is eventually the friction loss due to slurry. The friction loss due to slurry. 3 meter is the friction loss due to water, but 4.5 meter is the friction loss due to slurry, and you have used the correction factors. Okay. This is one method. There is another method which is known as the Hasin method. So, estimation of friction losses of clear water transportation through steel pipe, the alternative one. This is the Hasin friction pipe friction diagram, right. So, what you need to do over here is this: you pick up the pipe diameter is here, you pick up the pipe diameter. Okay. These are the pipe flow rates. These are the pipe flow rates. So, you select the pipe flow rate where it is coming. Okay. Then go there, touch the pipe roughness and go there as a friction head. Okay. And here is the C, pipe roughness C. What is the pipe? Now, for us, for the clear water, the industry standard is C equal to 140, C equal to 140. Hasin-Williams constant C equal to 140. So, in fact, we should have come to this level straight and then go there. Okay? Somebody is using 120, rubber 110, 130, basalt 120 to 140, steel 130 to 150, plastic 140 to 160. So, probably he has considered this is a rubber lined. So, if it is rubber lined, yes, 120, but normally when we do steel, then it is 140. If it is a rubber line, consider 120, right. Is this clear, this diagram? So, again the value whatever you will get friction head, this will be for the clear water, this will be for the clear water. Now, using the nomogram, it may be difficult for you all, because in a nomogram if you are at times lead to the inaccurate results, as actual position and intersection of the connecting lines may vary little bit due to human error. It may happen, because if I plot something and if you plot something, we may get some different results, it happens, but this is not desirable. Hence, following analytical model is preferred over the nomogram. So, this is the analytical model. You see here, see Hasin-Williams constant, you can put 140, use these things, cube meter cube per hour, and D is inchy, D is in inch, pipe dia, inside dia of the pipe in inch. If you use this formula, then you will precisely know what is the friction loss percentage for clear water, right. And once you know the friction loss, then you have to do this correction factor, percent solids by volume, use these factors, take it wherever it is coming. Now, it is getting like this. So, in fact 35% should be used for 40 and use this value, right. Multiply that with the clear water. So, you will get your slurry friction head drop. This is also another interesting thing. The slurry pumping require comparatively higher TDH than water pumping. We have seen that, you see, and it varies. And this has been tested, that for the same flow, the curve is like this. If this is the head, then the friction curves are like this. This is the clear water, then with 20%, then with 40%, and the heads are different. Heads are different. So, that is the reason we are so particular in terms of conversion of the water head to the slurry head in terms of the friction loss, while we are computing the friction loss, right. Now, we have seen some sort of these things as a duty point, system curve. Now, this is the water curve and this is the slurry curve. So, duty point shifts, right, duty point. Now, this is the one we give to the pump vendor. Pump vendor transfers this one to some point here. We must not give this one. This one we can compute and leave it to us, but to the vendor this is the point, meters of slurry. The question is why? Because this transfer is also an art. It may vary from manufacturer to manufacturer. Let us see how it happens. Now, you see here the conversion of the slurry head to equivalent clear water head for pump selection. Now, see here there is a factor. Then there is something we call the head ratio, HR, and there is something we call efficiency ratio, ER. Now, what is that? HR is equal to 1 minus K into CV by 20, right. So, you get a factor of this. Now, K, this is the K factor, this is the K factor. You can see the particle size, this is the particle size D85, right. This is the particle size, this is the solid specific gravity. So, you come to the solid specific gravity line from the particle size, go over there and select the K factor. Okay. So, as you can see, it is not very easy to do that. It is a typical example I have picked up where the figure is coming at 0.04, but if I want to do it myself, I may land into 0.06. The moment I do it, I will be out, right. So, it is better for us to leave this to the manufacturer, because they have got the right set of curves or the programs, they can punch in the numbers there to get the right value. But the methodology is this. So, in that methodology, what are the factors, what are the parameters that are influencing this? One is the particle size again, but this time it is D85. Can you just tell me why it is not D50? Anybody? Why it is not D50? Why it is D85? Because if it is a D50, then it does not describe the particle size distribution totally, but if I know the D85, I know bulk of the particle size distribution, right. The maximum part is known. So, all the influencing sizes are known, that is why it is D85, not on D50. Okay. So, specific gravity and this is important. So, now you can see the head ratio, it has become 0.94. So, H water is equal to H slurry divided by head ratio. So, the 26.5 meter slurry head is eventually equivalent to 28.2 meter of clear water head. So, this is how it is getting converted, right. This is again the same thing, conversion, particle size, but this method is D50 method by caves. So, I do not like this one, though it is prevalent in the industry, I could not ignore it thoroughly, but this is not a very, this is much of a conservative method, very much conservative, right, very much conservative, because number one, it works with D50, which is not the right thing. Second is that the factor it picks up, there is another assumption, there is this assumption is called the D50 by D, that is what is the impeller diameter by D50. This ratio before selection of the pump, very difficult to predict. So, they go by certain numbers to start with and they can fine tune it, but then number of iterations are required over here, and eventually wherever you are going, you see the figure 0.75, very high figure, that means the slurry head divided by 0.75, so it will be about say 30% more in terms of water head, unrealistic. So, the first method is much better one compared to this one, but still I would suggest that do not try to do that, just understand that it is done, it can be done in this manner, do not try to do that at all, leave this work for the vendor to carry out, because they have much more details and iterative processes available with them. So, we know the friction head of the pipe, that is known. Now, what is the length of the pipe? What is the length of the pipe? Let us say from the pump to the destination point, I say that this is the pipe which is going like this, like this, like that, like this. So, I say okay, the pipe has got 100 meters of straight run, fine, but then 100 meter of straight run, it is not like that, it has got number of bends, right. So, the moment there is a bend, there has to be an elbow. So, bend can be on a horizontal plane, bend can be on a vertical plane as well, right. Then it can have the T joints, it can have the valves, it can have the expanders, it can have the reducers, all these things it can have. So, then we got to also find out the friction losses for against each of them. So, this is the chart which gives you size of the pipe, and against that you pick up each, you will get equivalent straight head of the or the straight length of the pipe. Anything, let us say you are I am picking up plug valve, okay. If it is a plug valve, then say 150. So, this is equivalent to 2.1 meter straight length of the pipe, as if one plug valve is equal to an addition of 2.1 meter length to the total straight run. So, in this way you can multiply number of units with the equivalent one and you can come to some length. So, that some length when added to the main pipe length, that becomes the total equivalent length, TEL, total equivalent length. Total equivalent length TEL of any pipe system is the length of the straight pipe run between the origin and the termination plus equivalent straight run of the valves and fittings. So, you can see here there are different other areas, you know, expander, reducers, all are in terms of V square by 2G, some coefficients are there. So, you have to also calculate the heads for that, okay. Every cases are there. So, like this each and every item has to be scrutinized, has to be isolated, and against that the equivalent head equivalent length has to be calculated, then it has to be summed up. Can you see something? This is the suction side, right. We have seen that every pump discharge side is having smaller dia compared to the suction one, one step smaller. Now, you see here something, you see there something. If there is a concentric reducer, there is an eccentric reducer, we call flat top eccentric reducer, and this is a concentric reducer. Concentric reducer is avoided. Why? Because when the suction it is coming like this, there is a chance of formation of the air pocket and eventually drop in the flow, because there can be air locking. So, the preferred one is this one. So, flat top eccentric reducer is a must for the inlet connection. So, that means from here to there is one more size enlargement. So, between the pump discharge and the true suction, there is a two-step enlargement, is not one. One is from this to that and one is from that to that, okay. And this is a mandatory thing. Without this, suction will be very bad, very erratic, very bad. Now, it is the steps for computation of the total delivery head for the centrifugal slurry pump. What you do? Equivalent straight run of the pipe size needs to be computed for all the fittings and valves deployed in the total pipe route. Equivalent length we have discussed. Straight run of the pipe to be added to the EL to derive the total equivalent length of the piping system, TEL. Friction head loss as percent head in the pipe to be computed considering water transport using Hasin-Williams model with C equal to 140 for unlined pipe, C equal to 120 for rubber lined pipe. Figure thus derived is to be adjusted for the slurry of given consistency by multiplying the same with a correction factor. We have seen that. Friction loss thus computed is to be multiplied with the TEL. Friction loss is coming as percentage. That many meter per 100 meter of the straight run. So, how much meter for the TEL? So, that means friction loss thus computed to be multiplied with the TEL of the pipe to get the total friction head loss for the pipe route, HF. Flow rate to be divided by the pipe cross sectional area to get the velocity of the slurry in the pipe in meter per second. Now, slurry velocity head is derived by using V square by 2G. If cyclone is available in the system, cyclone pressure mentioned in kPa or the cyclone pressure head expressed in meters of water column is to be divided by the slurry specific weight to get the equivalent slurry head. Cyclone, people say 65 kPa. If I say 65 kPa and if I say that the specific gravity of the slurry is 1.35, right. So, that means 65 kPa is this much Pa, this is multiplied by 1.35, that is this into 9.81. So, that gives you HSL, some slurry head, right. So, it has to be converted to equivalent slurry head. Now, all the heads computed above should be added along with the static head. So long we have not discussed about the static head we discussed earlier. Now, all these heads have to be added with the static head for the system to get the TDH, total delivery head, requirement of the pump expressed in MSLC. What is that? Meter of slurry column, MSLC. Sometimes you will find MWC, meter of water column, and MSLC, meter of slurry column. Now, TDH in MSLC should then be converted to equivalent MWC by applying the relevant head ratios. I have shown you how to do that. Okay. Now, estimation of the power demand for centrifugal slurry pumps. People may say that okay, fine, if vendor is selecting this, he will be giving me the power. I said yes, he will, but beforehand when you are budgeting a project, you must also know that where the power can go, how much. Maybe one step here and there during the final stage can happen, but you have to come out with certain figures, certain numbers to start with. So, how to arrive at that? So, this is the way. The brake horsepower for the pump transporting water is PW is the brake horsepower, it is equal to head rho Q divided by 1.02 into hydraulic efficiency. Now, what is this density? And here the Q, it is in liter per second. From meter cube per hour you got to convert it into liter per second, right. H is the selected TDH of the slurry application converted to water head. Q is the water flow rate, liter per second, eta H hydraulic efficiency of the pump. What is hydraulic efficiency? You have seen the efficiency curves, right. So, by comparing, you can, to start with, you can say okay, I will consider 72% efficiency to start with. Eventually it may lead to 78% also, but to start with do not take the high figure, take a little bit lower figure to start with, so that your numbers are bigger and you can enjoy the credit of saying oh, I have reduced the numbers when the actual project is getting commissioned, right. Now, this is the clear water. Now, what to do with the slurry? Do not do anything, just multiply with the specific gravity of the slurry. Multiply this power PW with the specific gravity of the slurry. You get the specific gravity power for the slurry transportation. This is the brake power, that is power at the pump shaft. Now, who gives the power? It is the motor, through the belt it is coming. So, just 15 to 20% margin is allowed for selecting the motor. So, on top of that multiply this one by 1.15 to see what is the thing coming. Then the next available standard is the motor rating. Okay. Is that one clear? Is that one clear? Now, I will be going to the froth. So, about the slurry, is that one clear? Everything is clear, or if you have got any questions you may shoot me. Now, one thing I have not discussed. So, let us address that issue, which is an important issue, and very often it is industry faces the challenge. Let us say this is the duty point, that is you have specified certain flow rate, let us say Q1 here and H1, and this is the design duty point. This is the design duty point. Now, when you are specifying the head to the vendor, what you do, the head that you have calculated, you add certain margin. Let us say 10% margin you have added for the pressure or the head, and 10% margin you have added for the volume, right, or maybe 5% for the volume, 10% for the head. That is the design safety factor you have added. So, against that he has selected and his operating point is here. But when that pump is being operated in actual, then this cannot be the point. Then the point would be his actual point is here, it is coming here, right. The actual point is coming here. That this is because of my design margin, actual point is here. Under that condition, what will happen? Suppose your pump does not have any speed variation, it does not have any speed variation, then what will happen? So, the pump first, what it will do? It is here. So, when it will be pumping this much, it will see no, it will not face that much of resistance in terms of head. So, it will try to pump more, it has got a power, it will try to pump more. When it will be pumping more, then when it will be pumping more, then it will come here at some point. So, this is the selected point, it will get the resistance up to this. So, it will try to pump more, but when it will pump more, it will see that no, my resistance is becoming more. So, it will again try to pump less. So, it will go here. So, again the head will go up, again he will say no, head is going up, I should pump more to bring down the head. So, the pump will shuttle between this point and that point. It will do like this with the flow fluctuation, okay, which is known as the hunting of the pump. It is very common in the industry, hunting of the pump, right. So, if there is a hunting of the pump, what happens? The flow fluctuates, the cyclone performance, if any cyclone is connected with that, the cyclone performance gets affected. It is a very interesting thing. You will find that normally, let us say a cyclone curve should do this, right, under a particular D50 it should do this. Now, because of this pressure fluctuation, it is changing the D50 point, it is doing this. Now the problem is this, these two things are happening at such a short interval that you cannot distinguish between this and that. So industry sees the curve going like this. This is a typical case of UCIL Jadugoda. They have shown us a cyclone overflow of this nature, which cannot happen. I said the sampling was wrong. He said no, sampling was not wrong. Then he took the logbook and at least 5 or 6 samples more or less showing the similar trend. Then the immediate thing, suddenly it appeared to me that how the pump is behaving. Then they said the pump is having problem. I said, is it hunting? He said yes. So it is that. So just you see the problem. Looking at this, he will try to blame the cyclone manufacturer. Your product is not performing. But is it the issue? No. Issue lies somewhere else. Totally different, somewhere else. So this is a very common phenomenon in the industry. Now what is the correction? Correction is that either you can throttle it, which is a difficult process, or throttling a system is always a difficult process, or you do a speed correction. You do a speed correction, right? So that is the reason pump with variable speed is a much better option. Pump with variable speed is a much better option. Okay? Is this clear? Now let us see let us come to the froth handling system. So what happens here? The pump pattern is different. Nowadays froth handling can be done both by the vertical pump as well as the horizontal pump. But in the earlier days it used to be the vertical pump only. So it is a sump pump type of thing. You see, it's a 100% flooded suction. Froths with 100% flooded suction, and it used to also get some ventilation point so that the froth air can be released, and the inlet used to be like this, impeller like this, and the pump casing like this. Normally those are the rubber lined froth ones. Duty wise, light duty, not a very heavy duty one. Some important rules for selection of the froth pumps. While considering the slurry flow rate, actual flow rate should be multiplied with an augmenting factor known as the froth factor. This factor takes care of the additional apparent volume of the slurry that the pump needs to take care of due to the presence of the froth bubbles in the slurry by selecting higher operating speed of the pump. Because when you are pumping froth, say 100 meter cube of froth may take a volume equal to 200 meter cube of something of the slurry, volume wise. So what you need to ensure that they come very fast, right? So speed is the important criteria here. Speed is the important criteria here. So what you do, you multiply the actual flow rate with a factor known as froth factor to come to a virtual flow rate, right? While computing the frictional head loss, 25% additional volume needs to be considered, as that would take care of the released air in the slurry after froth burst at the discharge end of the pump due to high pressure. All other steps in the friction head calculation would remain same as that of the frothless slurry. So these are the two things. That means Q has to be Q into froth factor, and the velocity or the volume that we will be considering while selecting the pipe and the frictional head loss, that would be 1.25 Q. Why 1.25 Q? Because when the froths burst, it releases air. So the pipe has to have some space for holding the air. There was a question, who made this question to me, that what will happen if there is air and this thing slurry transportation together. Somebody made a question in the morning. So I said that I will come to that. You made this question. Now you understand what is happening. You understand? Value of the froth factors depending on the type of the froth being handled. Now, there can be different type of froths. There are tenacious brittle froths which burst very easily. There are very tenacious froths which it becomes very difficult to kill them, right, and there can be medium froths. It depends on what froth from the what mineral. While estimating the brake horsepower of the pump, actual flow volume and the head should be considered. However, hydraulic efficiency of the pump to be selected from the curve considering higher flow rate and speed of the pump against the actual head. Is it clear that what I am saying, that I have considered, let us say I have considered froth factor 2, that means twice volume. So, twice volume into the head, it will take me to some different speed level of the pump at a high speed. Now, shall I consider twice volume while doing the power computation? Never. Power computation has to be on the original volume and the original head computed, right? Original head computed. But only thing is this, the efficiency has to be considered from the higher speed range. Then all other things are similar to what we have just learned for the slurry pumps. Okay. Now you can see here, this is the frothless H versus Q, and this is the froth pump curve, characteristic curve with the air. Okay. But in the operator's manual or in the vendor's manual, nobody will give you the curves like this. They will give you the curves like this. You got to compute the equivalent thing by adding the froth factors, etc. But in reality, this is happening. So, system with no air, it is there. System with air at discharge, it is there. So, you see, system with air at the suction pressure, it is coming here. So, the head is decreasing. The typical values for the froth factors, as I was telling, different types of froths are there. Copper rougher concentrate 1.5, copper cleaner concentrate 3, molybdenum rougher 2, moly cleaner 3, zinc rougher 3, zinc cleaner 3.5, coal 6. But these are the things only for the vertical slurry pumps, not for horizontal, vertical froth pumps, not for the horizontal one, because we have been discussing the vertical froth pumps. So, these are the froth factors for that. Okay. But we have seen that by taking this, pumps are getting sometimes too big unnecessarily. People wants to play safe, and in the process they adopt these things. Something should definitely be adopted, but these are the high figures. So, eventually the selected pump is more, motor rating is more, everything is unnecessarily bigger. So, the current trend is to use the horizontal pumps, froth pumps. Horizontal centrifugal pumps can also be used in froth pumping with new concept of tested froth factor. What is tested froth factor? As NPSHA in the froth pumping is very low, it was a challenge for the centrifugal pumps to cope with the flow versus head condition with very low NPSHR, because it is already having froth. So, NPSHA obviously low. So, NPSHR has to be even lower than that. So, that is to be a challenge. With the advent of the new generation horizontal pumps having impellers with wider vane passage width and high ratio of suction to discharge, right, discharge diameter in the pump, it is now possible to use the centrifugal pumps to operate at a very low NPSHR for relatively higher speed of operation. As per the new school, froth factor is the ratio of the aerated slurry volume to the airless slurry volume. That means I collect slurry, I see the volume in a graduated cylinder, I see the volume, I leave it like this. So, when the bubbles go, then I see what is the volume, right. So, ratio of the aerated slurry volume to the airless slurry volume. So, That is the actual froth factor, which is scientifically very correct logic. So, which is equal to 1 by 1 minus psi. So, the 1 minus psi is the percentage air, initial slurry volume minus final slurry volume by initial slurry volume into 100, that is the psi. So, it is 1 by 1 minus psi. So, for brittle froth, froth factor equal to 1.1 to 1.25, for medium froths 1.25 to 1.5, for most tenacious froths froth factor is 1.5 to 1.8, where we are talking about 3.56, you see it has come down. So, the selections are all very economical and much effective. That is all.